Currently, there is a global pandemic of COVID-19. This disease has a death rate of 1% and a very high infection rate, meaning that it'll be of utmost importance to prevent its spread and eradicate it. Some ways in which we can help reduce the infection rate is by wearing masks and maintaining distance from each other, otherwise known as social distancing. This is because masks prevent droplets from going in the air, which could potentially make another person ill. The social distancing also reduces this chance. The enforcement of these rules is very difficult, so improving this is of the utmost importance in reducing the spread of the virus and getting things back to normal. This project aims to create a neural network that can detect whether a person is wearing a mask and also if they are wearing this mask correctly. It will also be able to determine whether people are practicing social distancing or not, and keeping 1.5 meters distance from each other, which is the set guidelines. The network must be accurate and have a high mean average precision so that it is effective. This will address the problem as it could be used to identify which people are following the guidelines and which people are not, which could then be enforced. To begin with, we will look at how I created a network to find whether a person is wearing a mask or not. Transfer learning is a method to be able to train accurate object detectors when the dataset use is limited. This is because for deep neural networks, a lot of training information is needed to create accurate results. There are pre-trained networks which have been trained on large datasets such as Microsoft Cocoa, which contains 80 classes ranging from people to cars. To detect a person, a network may look for facial features, which could show that there is a potential person in the image. Mask detection would also look for a face, as this is where the mask is located, meaning the two problems are quite similar, as the features found in each would be similar. This allows us to create an accurate object detector, even though our dataset is not very large. Neural networks are very computationally expensive. However, with the introduction of convolutional neural networks can become much deeper while still being able to perform at a modest speed. They are made up of tensors, which are 3D matrices of shape width by height by depth, as we can see here in the image. The original size of the network is given by the image, and later the size is given by filters. These filters are a way for the network to determine what feature it is looking for. This could be a horizontal line, or it could be a certain color, which different filters would be looking for. These would then be convolved with the original image to create the next layer. The more of these layers we use, the deeper the network becomes. The deeper a neural network becomes, the more abstract features it will extract. For example, in the first few layers, it could look for a horizontal line, while in later layers, be looking for a shape that resembles an eye, which would also have earlier features such as a circle or for specific colors. Features such as faces would benefit from deep networks due to the complexity of them, and as a network gets more complex, the more abstract features it can get. I use the faster RCNN network as my architecture, which I would then use transfer learning on to create a network able to detect people wearing masks or not. This is because the network has a high accuracy and it still can run at roughly 5 frames per second. To begin with, I trained on the final layers of the network, as this is common in transfer learning problems. But then I also decided to train on the full network to see if the accuracy improved. I found that the mean average precision scores, or MAP scores, for each were roughly the same, and this didn't make a significant difference. The small improvement of around 1% could be due to overfitting of the data. The faster RCNN architecture works by using a classifier to find potential regions of interest, which could contain objects. These regions of interest are then filtered so that only those which contain objects and are properly bounded are given as an output. This allows the network to be very accurate and still maintain a good frame rate. To find out whether people are practicing social distancing or not, I first ran an image through the neural network to detect people wearing masks, so I knew the location of these. I then warped the image to a bird's eye view using OpenCV, which is a computer vision library found in Python. Once I had these locations, I took the Euclidean distance between all the points and classified the points whether they were practicing social distancing or not. I then plotted these points on a black background with the circles of 1.5 meters around them, where the green circles show people are socially distancing, and red circles showing that they are not, maintaining the 1.5 meters distance. I then unwarped the image to show 1.5 meters around the people in the original image so that we could see which people these were corresponding to. The network was successful in classifying whether people were wearing masks and could accurately determine whether people were social distancing. It runs at roughly 5 frames per second when I used a webcam, and the network is running on a GPU. The YouTube link here shows a short demonstration of how the network works with a video. In the video, we can see in the top left the original video. In the top right, it has the social distancing detector, and it shows whether people are distancing or not. In the bottom left, there is the mask detection, so the neural network working on the masks. And in the bottom right is the combined image of both the social distancing and mask detection. After training for 25 epochs, the mean average precision of the network on the train set was 84.9% and 79.7% on the test set. This discrepancy is most likely due to overfitting of the data. This is a very high mean average precision. However, when we look at the graph, we can see that maybe more training, there is a slight trend upwards on the first epoch and then stops and fluctuates around 85% for the training set and 80% for the test set. Any further training could increase the map, however, it may also cause the network to overfit significantly. To improve accuracy, I could make a larger data set or use image augmentation, which is a way of making the images different, such as rotation or color changes, which can make the network a bit more robust. And this would also make the network dataset larger. The training loss steadily decreased, however, it does not reach a plateau, indicating that more training could be useful to improve the network. In future work, using a different network architecture could help improve the accuracy. However, this could also cause the network to be slower than it currently is. A system could be built using a camera and a lightweight device, which could be mounted then in a shop or known location. And then we could test this system out in a practical environment to see how feasible it would be in enforcing the rules. This would then require building this network on a lighter architecture, which would allow it to run at a higher speed, but also on a much more lightweight device, as currently it's running on a GPU, which is very large. And to improve the social distancing aspect, I could reduce the dataset. Redo the dataset to include the classes of masks, not wearing masks, and masks worn incorrectly, which are in the original dataset, and add a fourth class of person, so that the network could be more accurate in finding whether people are practicing social distancing or not. Overall, this network performs very well, and it is able to meet the project aims.